Hello everyone, and welcome to the live stream. My name is Michael Breddy. I'm the founder of Applied Ion Systems. Today we are going to have a look at the newest thruster system that I've built or designed, the AHT1-PQ. So this is the second live unboxing that I've done for my thruster systems. So this is a very special thruster. I've been working on this system for quite a while now. Actually, this has really been the goal of the entire ADAMANT series. This whole development, working with adamantane fuel, has been building up really towards the extreme miniaturization of conventional gas-fed electric propulsion technologies. So Hall thrusters, gridded ion thrusters, stuff like that. From my prior work, if you've ever followed it or been following it up to date, I successfully tested the first generation Hall thruster, the EHT1, which was a Micro End-Hall Thruster. And moving forward, this is the newest system, the newest next generation for these Hall thruster developments. And there's a lot of unique things that have gone into this thruster system, which I'll get into shortly. So really quickly, before I begin, I just want to give a big shout out and thanks to all of the AIS patrons and supporters and donors and contributors. Really, this entire effort is fueled by everyone who contributes to this, and developments like this would absolutely not be possible without your support. AIS doesn't have any source of grant money, any investors or funding. Really, all of you are all the investors and allowing for me to continue to develop propulsion openly and providing resources for the community. So I really thank everyone again for all your incredible generosity and allowing me to develop these systems. I want to also give a big shout out to Xometry, where I get these parts machined. It's been absolutely fantastic working with their system, with their online services, and working with their engineering, their design engineers. Specifically for this, I had to go back and forth with a few design changes to really tweak the manufacturing to get it right. So Xometry has been a huge enabler of all my developments for quite a while now. Then I want to also give a special shout out to the Lee Co., who has generously sponsored AIS with one of their Iep Series valves. This valve is a micro valve, which is crucial for this development, and actually one of the most important parts for this whole thruster system that has really allowed me to develop this system at such a small scale. So again, thanks to everyone. And to everyone who is tuning in and joining to see this live stream. The live chat is open, so feel free to ask any questions whenever. I'm sure there's going to be somewhat of a lag between when I see them and when I answer, but I'd be more than happy to discuss anything or any of the concepts or anything while I am going over these systems. So a little bit of background. Moving forward from the prior system again, this was the original Hall thruster build. This was the EHT1, so the first generation Hall thruster from Applied Ion Systems. So this has everything. This has the fuel tank, this has the power electronics, the thruster head itself, and the neutralizer. With this development, one of the big issues has been valving. I haven't been able to actually properly develop valves for this. And you can see here this white band is where the valve housing would have sat. There was multiple attempts to develop valves myself, and those were unsuccessful. So moving forward, having especially the Lee valve has been a major necessity for this design. So this is about 1/3 of a U in total volume. This thing was operated both with a tungsten filament neutralizer and with the GDN1 cold glow discharge neutralizer. So I actually ended up achieving ignition several times with this, and I believe it was the first time that a Hall thruster has been reported to be operational with adamantane fuel in the EP field. So a lot of really cool stuff has been done with this particular thruster system. Moving forward, there's a lot of key issues that the new system addresses that this one has a lot of issues with. The first is the fuel tank. Actually, within this housing, which is 3D printed, there's a really small fuel cartridge, which if you've seen pictures of this development, you'll have seen it's a very, very small little canister that holds only about 3 grams of fuel. The new thruster, however, holds about 18 grams of fuel in the same form factor, so a huge increase in fuel capacity. I found that with the 3D printed housing and the seals in general, it couldn't seal well for vacuum conditions. So there was orders of magnitude higher leakage into the vacuum system than they're supposed to be. And besides the fact of not having an actual valve to work with, made testing quite a challenge. So as kind of just a really brief review before I go into these systems, for the prior builds, the EHT1, it's again an end-hall thruster. So here we can actually see a cross-section of the end-hall thruster itself. So we have the anode here, we have the upper pole piece, the steel base, there's magnets embedded all around inside. The gas flow channels, so gas flow comes up through here. When operating, there's a couple of modes. You can either have a tungsten filament or you can have some sort of hollow cathode. Both of these provide a source of electrons, so these are either thermionically boiled off from the tungsten or emitted out from the plasma from the hollow cathode. The electrons are drawn into the thruster through the high potential from the anode. There's a magnetic field, so here we can see one of the magnets. North is going to the top, south is going to the bottom, and then for the magnets on the side, we have north on the bottom, south on the top. So that way we create kind of this magnetic loop through the thruster, which connects out through in this particular fashion. So this allows for increased ionization collisions with the electrons to ionize the gas. The magnetic field here is actually quite weak because it has to jump pretty far between this magnet and the end of the pole piece. So ionization efficiency of end-hall thrusters are quite poor. And because of that, and overall in general, end-hall thrusters are quite low efficiency. And actually you don't see end-hall really used at all in EP for propulsion. One of the biggest efficiency losses with end-hall thrusters or end-hall sources in general is the discharge current to beam current conversion. For end-hall technologies, it's about 20 to 30% conversion efficiency. So if you have, let's say 1 amp of discharge current for the main discharge, only about 200 or 300 milliamps will actually be converted to beam. So you have massive, massive losses. In addition, you also have very wide plume divergence with these types of technologies, usually 40 to 60 degree divergence, which also introduces significant losses. And then the lower magnetic field strength in here also reduces the ionization efficiency. So with that, with the wide energy distribution of the beam and all these losses, end-hall is actually quite poor for electric propulsion. It's fantastic for the manufacturing industry, so if you're getting into semiconductor manufacturing or surface modifications, this is a great technology, but it's not really optimal for hall thrusters itself. Now, I use this type of technology because it was very, very simple to build, very easy and cheap, and it allowed me to start exploring this immediately. And I was originally going to go with an anode layer prior, but I didn't quite work out the actual anode power feed. So you can actually see here, a wire comes through and connects here, and there's an insulator and a feed-through spot, and then somewhere to clamp the wire. So working out this, I was able to move forward and have better ability to actually connect to the anode, which was quite challenging, this particular topology, just the overall scale and setup of this has been quite a challenge to get everything where it is. But this actually also uses off-the-shelf ceramic washers from McMaster-Carr, and then just a few of the machined parts for the thruster itself. So I'll actually come back to this once I start unboxing the thruster and kind of show a side-by-side comparison between the old one and the new one. So let's actually get on to the unboxing. Also hello to Tejas Shenoy, thanks for joining, and also Yuli as well. I did end up tweeting this just prior to actually starting, so generally I don't expect that much of an audience, but at least it gives people an opportunity to kind of tune in and see these types of systems, because in electric propulsion this is extraordinarily unusual. It's actually completely unheard of being able to see thruster systems intimately like this, and I've never seen this system in real life myself. This is the first time I'm literally opening it up, so you're going to be seeing it right at the same time as me. Now for this thruster there are a bunch of components. There are several quite a bit more parts than the prior one. However, the build itself is very, very similar. The actual thruster casing is quite similar, the outer diameter is similar, and the way that the anode and the fuel baffle and housing all sandwiched together is very much similar, just a little bit of modifications with the internal components. So let's see what there is first. There are two major parts of this build that actually have come in. There's the actual thruster itself, so that includes the thruster housing, the pole pieces, the anode, and then there's also the fuel casing. And the fuel casing, I decided with much difficulties from the prior 3D printed ones, I ended up going with a solid machined aluminum housing, just because I need, in order to have higher reliability, I need this system to be very, very leak tight, and the solid machined housing would really afford me that. Much better than the 3D printed housing, and it also allows me to easier integrate the actual fuel valve directly into the tank itself. So I'm not actually sure what this first part is. So once I get this open, we're going to start seeing what this is. And this whole entire Hall thruster system is incredibly small. The entire dimensions are 42 by 42 by 56 millimeters. So that's for everything. That's for the fuel tank, that's for the valve, that's for the Hall thruster, and for the electronics. And one of the unique things about this Hall thruster is it's also run in a neutralizer-less mode. So I can completely eliminate the neutralizer power supplies and the neutralizer itself. I'll get into a little bit more of how I'm able to achieve that kind of with the unique way that I'm operating this thruster. So as far as I'm aware, this is actually probably the smallest full Hall thruster system that's ever been designed and built, about 20 millimeters in diameter. But the actual Hall thruster system as a total is only 0.1 U. For everything, which is about 10 times smaller than I believe the smallest commercial Hall thruster system out there. It's rated for less than 10 watts of power, so 2 watts of discharge, and then probably 6-7 watts of heater power, and then another watt for the electronics. So it's actually, which allows it to actually be the first and currently only Hall thruster compatible down to PocketQube class systems. So now this thruster has gotten into scaling where not only 3U, 2U, and 1U CubeSats can implement Hall thrusters quite comfortably, but now we're talking about 3P PocketQubes being able to handle operation of Hall thrusters absolutely beautifully. One of the things I'm always worried about is if I mess up specking out the threads for the holes and stuff, but this looks like it came out absolutely fantastic. So this is solid aluminum. I forget which one it is exactly. It's part of the 7000 series aluminum, so a bit stronger than the typical 6061 or 6063. So there's a lot going on with this particular tank. So inside we have enough capacity for about 18 grams of adamantane fuel. So there will be a presser plate and a spring that presses it down. On the back side, there's actually a little machine pocket for the metal ceramic heater. So it's the same type of metal ceramic heater that I used in the prior build. However, this is a larger square version to give me more coverage. There's a little feed channel that connects from inside of the tank to the fuel valve, and the fuel valve itself will actually sit right in this pocket. So the fuel valve goes into the housing itself. Ideally, when putting this together, it would be best to have the valve stem actually welded to the housing, but for now I will be using ultra high vacuum compatible epoxy. I found some really great UHV epoxy that's good to 10 to the minus 10 torr and up to 500 degrees Fahrenheit. So that'll be actually do very nicely for seating the valve into the actual slot. So we have the upper seal here for the tank cover and adapter, and then there will be another seal that compresses up against here. It's actually a really good question. This prior week, I actually ran full tests on the electronics. So I don't have the soldered board with me now. That's actually currently in the vacuum chamber. But I did benchtop tests of the fuel valve circuit. So the fuel valve circuit is fully functional. And I did high vacuum breakdown tests of the high voltage side. So I ran the board up to 3 kV, which is significantly higher than where I would run it at. Typically, I'm looking at a range of about 600 to maybe 2 kV, depending on what works best for operation. So at this point, the electronics are fully qualified and tested. Actually, tonight, after this live stream, I'm going to go ahead and start doing a full pre-assembly just to do all the checks and everything for the assembly-wise. And then I'm looking to start the final assembly and wiring over the next couple of days, and hopefully run the first ignition test on power and firing this thing in vacuum. So hopefully already by Saturday we might be seeing beam from this system. And assuming everything goes well, I will run the system for as long as the fuel allows me. And from prior tests, I was able to get about 1 hour per gram of adamantane with no valve, so just open flow on everything, running at higher temperatures than I'd probably like. So I'd like to optimize it a little bit more. So I'm hoping that at least this thruster, at least with the 18 grams or so, and the spacing and everything, to be able to run at much lower fuel flow rates, I'm hoping to get at least 20 plus of hours of operation for this particular thruster. So quite a bit longer than my prior builds. And working out the calculations for delta V and for the total impulse and stuff, that actually gives quite a good, a little bump for nanosats and picosats, especially at the low Earth orbits of the 500 to 600 kilometer range. So for this thruster, I'm expecting about 20 to 50 micronewtons of thrust, and that all depends on the discharge supply. I'm using a 2-watt Pico supply. So depending on the final output voltage, I'll have more or less current to work with. And hopefully, if I can get ignition down to 600 volts, the 600 volt Pico will probably provide me enough discharge current to be able to achieve about 50 micronewtons of thrust. So here I actually got 2 fuel tanks machined. I was originally planning on doing a test, one without the fuel, without the valve, one with the valve, because out of all the parts, the Iep series valve is quite expensive. It's the most expensive piece, so I didn't want to risk it, but I figure it might be worth testing the whole system as a single unit, just so that I know that everything is working. So I got these 2 guys all set, and they look absolutely fantastic. Again, I'm really, really happy with how these came out. So I'll just set these aside here. And then let's move on to the next part. So again, for anyone just joining, currently unboxing the EHT1. We just got through a little bit of a preliminary start on some of the basics, and then starting to unbox some of the first pieces now. So I'm kind of just going randomly. I don't know which parts are which. And let's see, this one seems like it's probably one of the Hall thruster parts because it's wrapped in oil. And the actual thruster housing itself is machined out of 1018 steel, just to give me a higher iron content for the magnetic circuit. The anode is stainless steel, and then the actual fuel parts are all aluminum. So now that I know that this is a part of the Hall thruster head, I'll just probably set that aside and then do the tank first and then work my way to the actual Hall thruster. So let's open up the next piece. So another question from Tejas, what are the changes in the electronics with regard to the End-Hall? So that's a really good question. So the biggest change, well, a lot of the change relies on the fact that the two systems are very different power classes. The EHT1, the original Hall thruster, was a 20-watt class, so that used actually a 9-watt Pico supply. So this is the discharge supply, and then this board had the supply for the hollow cathode. Because the new EHT1-PQ thruster runs without a neutralizer, there's no neutralizer power supplies, and because I'm operating at less than 10 watts, I'm using just the 2-watt Pico supply. So this electronics system is very, very simplified. Out of all the thrusters that I've built, this is probably electronically the most simplest and hopefully reliable system. I expect to just be able to turn this on and fire it, and it should be the easiest thruster to just get working and actually control. So this looks like it's probably part of the tank. So we have, let's see, yep, this is one of the tank pieces. So this is actually the bottom of the fuel tank. So you can see here there's actually a little pocket. This is for a wave spring, so this is a compression spring, which the heater actually sits right over. So that compresses it directly to the bottom part of the tank here for heating. So this entire thing gets assembled like this. And another part of this is also, this provides sealing for the fuel channel that goes from inside the tank to the inlet of the fuel valve. So there will be an O-ring in this little pocket here, which will be compressed for sealing, while also simultaneously compressing the heater against the whole tank. And what you'll actually see, there's a channel routed here and a channel routed here in the back. So I actually put these channels all along the entire assembly to allow for wire routing. So that way the wires will be kept within this 42 by 42 millimeter form factor and allow it to be much more neatly run back, because when the thruster is pointing out, you'll probably have the control lines coming back into the satellite. So they'll actually, for final assemblies and for final systems that get shipped out, they'll probably be epoxied into this channel with the ultra high vacuum epoxy, just to keep them in line. So this is about 2/3 of the tank now. So again, another aluminum piece. Beautiful job by Xometry. So we'll set these two guys aside here. Next, we'll get on to other part. So there's still two more parts to the tank. There's an upper fuel cap, which also adapts to the thruster head assembly itself. And then there is the fuel presser plate, which presses the fuel into the heated bottom. So this design takes a lot of inspiration from the prior EHT1 design, but I achieve much higher fuel density and hopefully much better sealing capacity. Okay, so this is actually a Hall thruster piece. This is the gas distribution baffle. So I'll actually put this aside for now and wait to go over that when I get into the actual Hall thruster build part of the unboxing. So this is also, I can tell by the drawings, this is the, I believe the upper pole piece. So I'll just cut this out and then put that aside for now. Yep, so again, this is another 1018 piece to complete the magnetic circuit. So I'll set that aside. And here we have, this is the upper part of the fuel tank. So this part is very important. Like other parts of the design, it provides multiple functions. It provides sealing on the upper portion of the tank for fuel feeding, but it also allows me to directly adapt the tank to the Hall thruster head itself. So the way that this is designed, this is again very similar to the EHT1, where everything is in line, so there's no fuel feed lines or anything. It's all directly in line from tank to the thruster itself to keep the system as compact as possible. So here we have the upper fuel tank piece. So what we have is, let's see if I can get that focused in. So there is a feed channel that goes from the outlet of the valve to the actual thruster feed holes. There is an upper seal here, which seals against the bottom of the thruster. And then on the bottom is flat, which mates up and seals with this groove. So the entire assembly gets bolted together like this, and the bottom piece gets compressed. So this is actually the full housing assembly. So you can see again, this is actually most of the depth of the Hall thruster itself. This is quite compact little fuel system. So, and the way that it's made is that I can bolt this all together here. I can bolt this all together on the bottom here without any bolts sticking out. And then there are additional blind tapped holes to adapt the Hall thruster head on top, and then holes on the corners for the circuit board. So this is the entire fuel tank assembly. Again, looking at it, everything looks really, really well made, really fantastically done. So you can see a lot of my designs, in order to keep the system super compact, they're multifunctional and they have a lot of features machined into them to be able to keep the system compact. So fuel feed lines are actually machined directly into the plates, which are used for both mounting, for sealing, for adapting. Another question, will the fuel tank need insulation? That's actually a really good question, and that's something that really I'll have to figure out through testing. With the prior tests, I've run 9 tests so far with Adamantane, everything from preliminary ionization tests, 4 of them, to 5 ignition tests with the Hall thruster and the hollow cathode. And Adamantane, I find it sublimates very, very easily at very low temperatures in vacuum, which is why it's such an ideal candidate for alternative fuel for propulsion. So I could see sublimation down to 11C ambient inside the chamber, although realistically better feeding starts at around 15C, and then increasing the heating rate increases the fuel flow rates. Because of the spacing of the Hall thruster anode and casing, which is sub-millimeter, I expect that I should be able to ignite the thruster itself with fuel flow rates. So that's ideally to be able to run the heater power at less power, and then being able to run it at lower temperatures, making the system more efficient in terms of the power side. However, that being said, because it's in space, it's going to experience extremes, and I'll have to actually really play around with how it operates and just how low temperature this thing will actually successfully feed and fire at, and what the thermals will look like. It might be that I might need some insulation, so Kapton insulation around the tank body. And usually when you see thruster systems, particularly any thruster system, you're going to see spec'd for both storage and for operational temperatures. And usually those operational temperatures are maybe 10, 15 C up to maybe 60 to 80 C. So there is still kind of a range where it's ideal to operate any thruster system. So it might be that depending on how it all plays out, the user may have to just operate the thruster when it's not freezing. But I'll have to really play around with it. And that is one of the big unknowns of the design. Now for higher power and for hopefully this system, because the Hall thruster is directly machined into the mounting flange, which is directly bolted onto the tank, it will wick heat away from the thruster. It'll act as like one giant heat sink. So hopefully the tank will actually warm up a bit while the thruster is firing. But it's always cold starts that can be quite challenging, especially for these types of fuels. Either water fuels or sublimation fuels could be a little bit tricky. But again, because Adamantane sublimates at such low temperatures, it does give me an advantage that I could start up maybe a little bit cooler. But we'll have to really see. Again, there's just a lot of testing, and hopefully if the sealing and the ignition works on Saturday, then I can really start getting into more of the qualification and long-term kind of testing of this whole thruster system. So opening up the next part, let's see what this is. So this is the final part of the tank. This is the fuel presser plate. So this is just a very simple aluminum plate shaped like the interior outline of the tank. So this just goes in just like that. There will be a spring, and I'm going to be using a conical spring that actually allows me to get the profile just almost completely flat to maximize the amount of fuel storage. So that'll actually just press up directly against that and continue to press the fuel into the heated portion as it's sublimated and used up during operation. So this looks like it fits really nicely. A little bit of a gap to allow for just actually fitting this in without jamming. So that right there is the entire fuel system minus the valve. And while I'm here, I might as well pull out the valve just to kind of show, for those who haven't kind of been seeing the updates and stuff on Twitter or other social media, kind of what the valve is I'm talking about. So this is the Iep valve itself. So really, really compact, tiny little valve. These valves are actually really, really impressive. There's a couple of different options. They can operate at 12 to 24 volts. There's an 800 PSI option, which is the one that this is. They can also go up to a couple hundred degrees. Well, I'll have to double check, but there is a higher temperature valve and a lower temperature one. This is the higher temperature one. I don't expect this system to get up very high in temperature, a few tens of C. Probably more than enough for sublimation, and then pressure will actually be negligible in this in operation. This valve is really just to seal off the vapors from escaping and to control the vapor flow directly into the thruster head itself. So hopefully I got my dimensions correct. So this fits right into here. And yep, that scared me a little bit. But so we can see the tank here with the fuel port, or the valve port. We have the valve, so this will go right in to here and rotate in. So I have the connections here. So this is going to be really quite tight and tricky to actually do, and then the stems will have to be cut to the appropriate lengths on both sides, and then I'm going to epoxy the bottom in to be sealed. So that's kind of one of the reasons why I was thinking of doing just a test without the valve, just because this is a very expensive piece. I think it's about $600 a pot for valve, which, given the capabilities and the fact that they are becoming much more common in CubeSat propulsion systems and actually designed for in-space propulsion use, this is actually a really, really fantastic valve, and really I think the smallest propulsion compatible valve out there for vacuum type applications. So this is, all things considered, it's actually quite a nice price for the capabilities offered with this particular valve. So this sits up in here, and there will be a seal here that fits into this little hole, which the stem goes through, and that will allow me to seal on the input side and feed the fuel in through here. So now that we've covered the actual tank, everything looks absolutely perfect. I'm super, super happy with this. So now we can actually get into the actual Hall thruster build itself. So I believe that this is actually the Hall thruster. And it is a little bit greasy, just to keep it from going rusty. So I'll have to really thoroughly clean all this stuff before final assembly. Fortunately, I also don't have any paper towels here, but I do have some Tim wipes, so that should actually work out nicely. So let's get this guy out of here. Let's wipe this down. So this is it. This is the actual Hall thruster housing itself. So it's like the prior Hall thruster. It's directly machined into the adapter. So on the bottom, you can actually see the fuel feed ports, which match up exactly with this little circular machine portion here. So that feeds from the valve directly in. And I'm trying to keep the fuel feed grooves and areas as small as possible, just to limit a potential for recondensation in the system, which can be a challenge, especially with these solid sublimating fuels. If the overall system is too cold, they can actually recondense on the insides, which can cause issues. But under normal operation, I actually haven't run into that issue with my other one, only with really weird tests that I've run for fuel tank sealing and leaking. So as you can see, this again is very much inspired by the original design. So the actual Hall thruster itself is exactly identical, besides the little interior piece for the pole. So the outside diameter is the same, the hardware is the same, the magnets are all the same. So borrowing the concepts from the original design into this new one and modifying the internals for anode layer operation. So kind of going back, now we saw the original End-Hall thruster. So again, looks like this. We have the baffle, we have an insulator, the anode, another insulator, and then the upper pole piece. So here is a very similar type of stack up, except a couple of different changes. So there's a magnet and a central pole piece that extends up. Then you have a very similar type of gas distribution plasma baffle, a couple of ceramic washers, the anode, which is extended up a little bit, and then the upper pole piece. So unlike the original end-hall thruster, the actual casing is floating, and the plasma bridging actually, when there's ignition, occurs from the anode to the electron source. So for a neutralizer, for a hollow cathode, when the neutralizer plume is established and enough electrons are drawn in and the discharge is high enough, you actually have a plasma bridge that forms here, and then as the power is increased, you actually see it convert to a plume. And I actually have some documentation that and video that actually shows how it transitions from this plasma bridging to an actual output plume. So the ignition is a little bit more tricky here, and it requires higher gas flow rates and higher power levels and voltage to kind of get that to ignite, just because of the distance here. And the casing is completely floating, so this is not electrically connected to anything. In this case here, the casing is actually grounded. So the anode here, this orange piece that extends up, is at the high voltage potential, and then everything else in the casing is at ground potential. So here we have a very similar setup with the magnets. So we have North Pole here, South Pole, and then with the internal magnets, we have the North Pole on the bottom, the South on the top. So we have the circuit that comes through, and there's magnet stacks that go up. And this one actually includes more magnets, so the field strength is much higher. And then the magnetic field actually passes between this pole piece and this pole piece. So this little gap here comes back down and completes the circuit. So already we have significant much higher magnetic field strengths within this tiny gap here. And then between the grounded pole section and the actual anode, it's a sub-millimeter gap, so really tiny gap to allow for ignition at very low flow rates. So here there's actually no source of electrons to start the discharge. The discharge is started through the ionization of the gas and the breakdown between the very close high voltage pole piece and the anode. So there's a question: could you brief hardware, how it's assembled with the CubeSat? So that I think in terms of assembling with the CubeSat, that highly depends on the end user and their application. With how I operate, I design my systems as modularly as possible, so it can be easily configured to be able to be adapted to other systems. So chances are, if someone is actually interested in building or getting one of these systems for their satellite, I would probably work with them directly to figure out the best way of mounting. For this first prototype, I don't actually have any direct mounting points, but it could be quite easily adapted with a couple of flanges or changing up how it's bolted together on the bottom. So there are a bunch of ways that I could actually manage getting this adapted to the CubeSat or PocketQube itself. But it really depends, because each satellite is so different with their internals and so different with how it's set up, that having this option to be open per system allows people more flexibility in being able to use this. So back to this, we have the high voltage that comes in here. We have this at ground, so there's a discharge that can occur between these 2 points. And that's one of the things about about anode layer sources, is because the casing is grounded to the anode and the spacing is relatively close. At high enough voltages or high enough flows, the anode layer source is self-igniting, so you don't actually need an external source of electrons to create the beam, because you can get a discharge directly between the grounded pole and the anode. Another question: isn't a requirement that the magnetic field peaks at the exit plane and be absent near the gas entry point? So I think that really depends on the type of Hall thruster itself. You know, there's the most classic and basic type of Hall thruster is the stationary layer. That's the one that you see on probably 95% of Hall thrusters out in the field. End-Hall, again, isn't really used for for thrusters, but it can be. Anode layer is also a little bit different setup, and there are some variations like the cylindrical Hall thruster, which is kind of like a modified End-Hall, and then there's also this kind of weird variation called the Hemp T, which is a multi-stacked magnetic field that has alternating poles, rings of poles that goes up the discharge channel. So some kind of interesting properties. But for stationary layer, I think there definitely is a lot of optimization done where the magnetic field peaks. For this particular thruster, because it's so tiny, it's very, very difficult to do magnetic optimization, I think, at this size. For very large Hall thrusters, you have a lot more space to work with. The discharge channels are larger, so you can play around with things like magnetic shielding and changing the field shape and optimizing it. But for this one, it's just so small that it's very, very difficult to actually achieve stuff like this. And for this particular one, it's more about usability and accessibility versus optimization. And one of the big things in general with stationary layer and with anode layer that makes them so attractive for propulsion, besides they can both achieve very narrow beams, which is good for thrust efficiency. The beam current to discharge current ratio is very high. So unlike the End-Hall, which is about 20 to 30% conversion efficiency, the stationary layer and the anode layer actually achieves 80 to 90% efficiency. So if I have 1 amp discharge, I could probably achieve with good optimization about 800 to 900 milliamps of beam current, which makes them very, very efficient compared to other topologies. So for here, in this case, because the channel of anode layer is so short, you can't really tune the peak that well, whereas the stationary layer, they have much longer and deeper channels, so you can actually get the field to dip in and change and do better alignments. But for here, the channel length is literally just like this tip here, which is, I think, maybe a millimeter at most. So the field strength is concentrated really in this area. So an anode layer plasma forms right here on the upper portion of the channel, and then the ions are kind of accelerated out. And because I'm using permanent magnets, I'm also kind of limited to how things how the magnetic field goes through here. But for my purposes, I think the magnetic field strength is more important than shape. Just because overall, for scaling, one of the issues with scaling Hall thrusters is that when you go smaller, the field strength has to, or the discharge channel shrinks, the magnetic field strength has to increase significantly higher for better efficiency. So for here, the channel length is extremely short for self-ignition, and because that gap is so small, I can achieve very high field strengths, especially with a large amount of magnets in the steel structure. So another question, what's the advantages of adamantane over Teflon? So those are actually two very different fuels. Adamantane would be used for any type of gas-fed system like Hall thruster, gridded ion, RF plasma, whereas Teflon is really used for pulse plasma thrusters. So the pulse plasma thrusters being a pulsed ablative thruster. So it's not so much of a comparison between the fuels as it is a comparison of the technology classes. You're comparing now traditional gas-fed versus pulse plasma thrusters, and there's quite a bit of difference between those. And originally I started with a lot of developments with pulse plasma thrusters, and while they can be made much smaller than the Hall thruster, it's very, very difficult to make them reliable at very low power levels, and having a very long lifetime, not really from the fuel perspective, but just from the components. The main discharge capacitor is the main issue for lifetime, just because it's so difficult to get something that lasts for long enough. With the voltages that you're running at, with the discharge currents, and the size, it makes it really challenging. So still, between the Teflon and the adamantane, still very different, I think, in terms of technology classes and what they're used for. You could technically use adamantane for a pulsed plasma thruster if you had a pulsed valve injection. So if you use some sort of pulsed gas puff injector, so this type of valve, since it's actually a quite fast valve, this could be used for pulsed puff injection, which has been explored a bit with pulsed plasma thrusters, like water vapor injected pulsed plasma thrusters, gas injected pulsed plasma thrusters. But generally, you start to kind of lose a bit of the benefits of the solid feed and the simplicity of pulsed plasma thrusters when you start looking at gas or water injection for them. But it could be very well used just the same for pulsed plasma thruster. For a Hall thruster, unless you vaporize the Teflon and feed it in, you wouldn't really be able to use it quite the same. So, getting back to the build, we have, again, the old thruster, the new thruster, and like I was mentioning before, this is not the smallest Hall thruster head ever designed. The smallest ones I've ever seen are a few millimeters channel diameter, so the entire Hall thruster head is like maybe 5 millimeters, where this is like 20 millimeters. But the challenge is not so much Hall thruster head scaling, but it's scaling everything. Even with those tiny Hall thruster heads, they still use large conventional neutralizers, and with the tank and valves and electronics and everything, they still end up being 1U in size. I haven't really seen really any Hall thrusters geared towards being less than 1U total package volume, whereas this one is 0.1U. So scaling the Hall thruster head itself is actually quite trivial. It's fairly straightforward ion source. There's not really much to it. The real challenge is in the fuel feed, is in the valving, is in the electronics. That's what a lot of this design kind of affords with the adamantane. The adamantane allows me to shrink the tank size because it's solid storage feed. Unlike iodine, which is very toxic and corrosive, there's no material compatibility issues with adamantane. It's fairly benign and safe to handle and work with. So that kind of eliminates some of the special considerations for iodine. And then without the neutralizer, I can again shrink the electronics and the overall form factor. Now, I mentioned that this is operated in a neutralizer-less mode. So for typical ion thrusters, either Hall thruster or gridded ion or stuff like that, you need some sort of source of electrons to counterbalance the ion flow to prevent excessive charging on the satellite. In the case of Hall thrusters, that electron source is also needed for ignition. Typically, Hall thrusters are operated at very low voltages but very high currents, and thrust is directly proportional to the discharge current, which gets converted to beam current. So the higher the current you have, the more thrust you're going to get. So typically at voltages of less than 500 volts, you're operating in a non-self-igniting mode, which is, you can't really ignite the thruster lower than that. However, if you start talking about 1,000 volts, 2,000 volts operation, then you're starting to get into a mode where you have a lot of a lot better ionization, and you can jump the gap and ignite these things much more readily. Especially for anode layer sources, again, because the housing is grounded and the spacing is so close, that gap is very, very easy to jump with fuel flowing through it. So at voltages of over 500 volts, you can achieve self-ignition. Now, anode layers, just like end halls, have a lot of use in industrial manufacturing and semiconductor manufacturing. They're a very, very common and popular source for these types of technologies. And while they are operated sometimes with external sources, electron sources like a filament or a hollow cathode, more often they're just operated in a self-ignition mode. So high voltages, gas flow, they just ignite immediately and you have beam. And one of the properties of anode layer ion sources in industry is that they have the ability to be self-neutralizing. And this is achieved through a lot of secondary electron emission due to the bombardment of the casing from the ions. So as the ions are accelerated out and they hit the casing, you liberate secondary electrons from those impacts. And that can actually be used for a self-neutralizing beam. And this is actually particularly advantageous at very low power levels. So because I'm looking at very high voltages and very low currents, at very low thrust levels, it becomes much easier to create a more balanced beam with this type of self-neutralization. And really it'll all come back to actually testing in orbit how well this actually works, because this isn't a new concept for electric propulsion, but I haven't actually seen it employed for Hall thrusters in orbit yet. So it's a very well-known fact in industry, but it's not really taken advantage of much in electric propulsion for Hall thrusters. So another question, are there issues with adamantane getting deposited on the insides of the channels, and how do you clean? So that's a very good question, and that goes back to issues with condensation. So these types of sublimating fuels, they sublimate at very low temperatures, but that also means they can recondense under the right conditions. Both iodine and adamantane can do this, and I have actually seen a recondensation under some certain circumstances. Now, one of the benefits are that both of these types of fuels also they sublimate very readily in vacuum. So as soon as they're exposed to vacuum, they're going to immediately start sublimating. And with a little bit of heat, the sublimation increases quite a bit. So as long as if there is condensation within the valve, within the channels, then really it means that I need higher temperature for operation. It means the thruster has to be warmed up more. And eventually, even if there's some condensation past the valve, so in the channel that feeds the Hall thruster itself, since that part is directly exposed to vacuum, that will eventually sublimate away quite readily. Now, it could potentially clog the feed channels depending on the circumstances. So that goes back to potentially speccing out the thruster with a minimum temperature operation. So if there's temperature sensors on board the satellite, maybe limiting operation or ignition to 15C minimum or something before turning the system on. And that also can be mitigated through higher heater power or adding insulation like discussed prior. For larger Hall thruster systems, because the Hall thruster is machined directly into the channel, which will act kind of as a heat sink, which will be directly bolted to this to the tank. At higher power levels, actually operation of the thruster will help warm up the entire tank, and I think help overall with that particular issue. So I guess moving on to the next parts of the thruster assembly, we have this little guy here, and this is the gas distribution and plasma baffle. So and one of the things I should mention about this thruster is it wasn't really inspired by any builds in electric propulsion. This system was actually inspired completely by industrial systems. Industrial systems can be made quite cheaply, manufactured quite easily. They're very, very robust. And it simplifies a lot of the aspects of the design. And a lot of times what you see in these particular systems is there is a, and you'll also see sometimes in Hall thrusters themselves, is a plasma baffle that acts for gas distribution as well. So you can see that here, that's this first piece here, and there's a wave spring underneath that compresses everything together when the cap is on. So this distributes the gas up into the channels radially around the thruster. And this also acts as exactly a plasma baffle to prevent any plasma backstreaming back into the thruster fuel lines itself. So this is kind of a multi-purpose little piece. And this is, again, the same exact kind of design as the prior thruster, but modified for the pole piece in the center. So this guy fits literally right inside, and then the other pieces are kind of stacked on top of that. So this piece is stainless steel, just because it acts as the plasma baffle, so it'll be bombarded more directly. So moving on to the next pieces. So we have now the anode. So this design is, again, very, very similar to the prior one. It's just the stem that kind of extends up into the channel is a bit longer to account for a little bit of the geometry change. The anode is stainless steel. I don't know if the camera will focus in on that. Maybe not. Yeah, I'm not sure this will focus in. But again, the anode itself is very small. Oh, there it goes. So there's a little channel that's machined underneath for the wire connection. And then the discharge will actually occur around the tip of this and then to the actual tops of the pole pieces. So going back to the original design, the discharge will occur between here and the top here, forming the plasma, and that's where the ions are extracted from. So there are, I believe, a couple more pieces. Let's see. Kind of throwing the pieces all around here. So there is a cap piece that goes on top. And then there should, I believe that's actually it. Yeah, so there's one more cap piece. Oh, here it is. So this is the last steel piece. So this completes the magnetic circuit between the initial anode and the pole, the internal pole and the external pole. So this, again, was very similar to the original design, except it was modified a little bit to allow for more narrow beam divergence, and also to kind of anticipate for a little bit of the change in the geometry. So here we can see the upper pole piece. Let's see if that focuses in. Well, not so much. So there's a little gap here for spacing with the anode, and then there's the actual channel itself is a little bit of the internal edge, so it's only about a millimeter for the total channel depth itself. So this again fits right on the top here, which is bolted on. The larger holes will have the stacks of magnets. There are 4 0.1 by 0.1 size samarium cobalt magnets that stack up in each of these, and there are 8 channels, and then plus another magnet that goes in the center. So there should be a total of 33 little magnets that goes into this entire assembly, and this actually fits directly on top, completing the magnetic circuit for the thruster. So again, literally quite almost identical to the original design, except changed for a little bit for the new geometry for the pole piece. And actually that is the last, there is one more piece I am looking for, and that is the pole piece, which is this center portion here. So the magnet sits here, and there's this center piece that gets threaded in. So this is grounded, the outside is grounded, and the discharge occurs between here. And this is what completes the magnetic loop. I hope that piece was actually included. That would be not great if it wasn't, but I actually have the... So another question, are the magnets custom made? They are not. They're just off-the-shelf standard 0.1 inch depth by 0.1 inch diameter samarium cobalt magnets. I forget the store I bought them from, but I think it's only like $1 or something per magnet. So they're very cheap. And samarium cobalt, I think, while they have a little bit lower field strength than neodymium, they have much higher Curie points, so they can operate at higher temperatures than neodymium without losing their magnetic properties. And typically samarium cobalt are ones that you will see a lot for permanent magnet Hall thruster type builds. So looking at the sheets, there should be the pull piece. I probably should have actually counted packages prior to opening everything up. Let's see if I can find that. Yep, last piece was underneath all the other packing. So this is the final piece of the Hall thruster build. So we're going to open this up. So this pull piece, like the entire thing, is really small. This is also 1018 steel. So I'm not sure if this will actually zoom in or not. And I'll have to take some nice pictures of all this stuff afterwards with the light box and camera zoomed in to really get a better picture. Just because it's so small, I don't think I can actually zoom in. But there's a threaded portion here for fitting into the thruster itself. So this should screw in. Should screw directly in, completing the magnetic circuit with the magnet on the bottom, so that little pole kind of sticks out. And then there's the insulator stacks, the gas distribution baffle, and the anode that kind of all fit around it. So you have the baffle, and the anode would actually go in first, which sits right underneath the actual pole piece. So for the magnets, for the ceramics, everything is completely off the shelf. So all that's needed are just machining the actual thruster parts itself. And that was one of the challenges with this entire build, both with the prior one and this current one, is developing the Hall thruster without any custom ceramics. Because custom machining metal, anyone can do it. And it can be done pretty cheaply. But custom machining ceramics is quite a challenge and quite costly. So by using just off-the-shelf ceramic washers for the insulators and building the system kind of like an industrial anode layer Hall source or anode layer ion source, it allows me to really simplify the manufacturing process and really reduce the cost overall. So that is the entire system. So if we actually stack everything together, you can actually kind of get an idea of just the size of the full Hall thruster itself. So here we have one of the spare boards. So this is an unsoldered electronics board. So this actually fits directly over the thruster itself and gets bolted on in the four corners, and then this sits directly on top. So everything is in line, completely stacked together, and this is the size of the full Hall thruster system. Again, this is fuel tank, this is valve. This is the Hall thruster head, and this is the electronics. Again, 56 millimeters tall, 42 by 42 millimeters in size. So this is the entire system, very compact, very small, and my hopes are this opens up Hall thruster technology to really any nanosat and picosat team. Not only just from the cost perspective of making this over an order of magnitude cheaper than current Hall thrusters out there, but also reducing the size, the total volume by an order of magnitude, as well as reducing the power level enough that CubeSats and now even 3P PocketQubes can actually use. So this is actually quite exciting to see, and again, this is really the goal of the entire Adamantane series, is developing a Hall thruster or gridded ion thruster or those conventional type thrusters, a full system down to something that can be compatible at the PocketQube class. And if this works, scaling up becomes really, really easy. In electric propulsion, scaling down is the most challenging aspect in terms of efficiency, in terms of actual sizing and compactness and power and operation. It can be a real challenge to get these types of things this small. And once you have more space and more power available, you can scale up much easier. So I'm expecting this actual Hall thruster head itself will be identical for the entire AHT1 series. So everything from 2-watt class discharge for the PocketQube version all the way up to 50-watt class discharge and higher for the standard AHT1 series. So this particular Hall thruster would probably be good anywhere from 3P to 3U CubeSats. And then moving up towards the 6U, from 3U to 6U class, I'd start using a more conventional one with a larger tank, with a separate neutralizer and with larger discharge supply. But this is the particular system that I'm most interested in, just because it allows not only any nanosat team to access Hall thrusters, but also opens up off-the-shelf, super compact and simple to use Hall thrusters that labs can also use, electric propulsion programs, really anyone to just pick up a Hall thruster that you can fit literally in your pocket and just use. So another question, could you reiterate about the cathode choice and what did you consider using, thermionic or hollow cathode? So for the original system and for larger versions of the AHT1, I am using a hollow cathode, and this hollow cathode is quite unusual in the electric propulsion field. Standard hollow cathodes usually use some sort of dispenser cathode insert, so lanthanum hexaboride or some sort of material with a very low work function that liberates electrons more easily, either through direct heating of some sort of heater or through self-heating through the plasma discharge. Unfortunately, those types of cathodes get poisoned very easily with anything other than inert gases, so that wouldn't work well with adamantane. The other option for non-inert gases would be an RF plasma cathode. So instead of using a dispenser insert, you would use an RF excitation to excite the gas into a plasma, and then from that the electrons are extracted. Those generally tend to be a little bit lower efficiency, and you also have the complexity of RF circuits now to deal with. The technology that I'm using actually isn't used in the electric propulsion field. It's used more in the particle accelerator field. So this uses a cold glow discharge hollow cathode. So as the name implies, it's a cold discharge. There's no heater inserts, there's no dispenser cathodes, there's no RF. It's actually just a direct high voltage DC discharge. So typical hollow cathodes will run at super low voltages, several tens of volts. This one is currently operating at -3 kV. So it establishes a very high voltage glow discharge between, there's a hollow cathode here, which is literally just a hollow stainless steel cup with a little threaded piece on the outside. And then there's a anode electrode, which is just a stainless steel laser cut plate with a hole in it, and then an extractor electrode. So between the hollow cathode and the anode, which is at ground, it's several thousand volts to establish that glow discharge. And because plasma essentially has a zero work function, so it allows you to extract huge quantities of electrons very, very readily. And actually, plasma cathodes like this are the highest current density types of cathodes for any sort of electron beam source. You can achieve current densities of up to 10,000 amps per centimeter squared, which is absolutely insane compared to thermionic hollow cathodes, which typically run around maybe 10 amps per square centimeter. So huge differences in the ability to extract electrons. This technology allows me to actually scale very easily too. Thermionic emission cathodes, it's more challenging to scale super small and low power. And because this whole system needed to be 20 watts or less, I needed a cathode that operated at only a couple watts of power. So this cathode actually operates at only 2 watts of total power. To put it in perspective, for my first ignition test, I used a tungsten filament just across here, and that required 50 watts for ignition, whereas the plasma cathode only required 2 watts. So a huge, huge difference in terms of power and ability for electron extraction. So between the cathode and the anode, there's a discharge that's established, and then there's an extractor plate that's positively biased to a couple hundred volts that draws the electrons out. And then once that, or draws the electron, there's a plume that kind of gets drawn out from that discharge from that extractor plate. And with the high voltage applied to the anode in here, there's plasma bridging that occurs between the neutralizer and the actual Hall thruster head itself. And then as discharge power is increased, the plume formation occurs and you actually have beam acceleration. So again, this particular type of hollow cathode isn't really used in electric propulsion, but it allows scaling anywhere from sub-watt cathodes to megawatt class cathodes. Megawatt class being, huge pulsed cathodes at kiloamps of beam current. But the same principles apply anywhere from cathodes that are several tens of centimeters in diameter all the way to sub-millimeter diameter cathodes. The internal diameter of this cathode is about maybe 3 or 4 millimeters, maybe 2 to 3 millimeters, so it's still a fairly small cathode. And one of the things to note is that the smaller the hollow cathode, at least for cold discharge cathodes, the higher the gas pressure has to be. So that creates some challenges. And this one actually I'm going to be redesigning because ignition is still quite challenging because I have the cathode and the anode spaced too far in this. So for the next generation of this hollow cathode, I'm going to keep the spacing much closer and hopefully get ignition at much lower voltages. Now you can actually see a lot of discoloration on the back of this cathode, and this actually occurred during the final ignition test of this, where I established full ignition and beam with the cathode operating. This is actually due to thermal stresses. Apparently, when full discharge is running, and the Hall thrusters are actually running at around 15 watts of discharge power. The thermal stresses on the 3D printed body were so high that it didn't melt, it didn't char, but it discolored and caused thermal cracking. So I'm actually going to redesign the cathode and the internals for better heat management. So again, like I mentioned, this is actually a 3D printed housing. This uses Somos Perform. It's a ceramic embedded SLA resin. I've actually been using this a bunch now. I've used it for the ILIS-1 housing. I've used it for several parts of the original fuel tank. I've used it for the actual cathode itself, and it is honestly a really amazing material. It's now, if I'm going to 3D print any parts for thrusters, it's probably going to be with Somos Perform. There isn't any data for it for vacuum, but so far it seems like there's negligible outgassing. It has very high dielectric strength. It has very high thermal capacity. And it doesn't char or burn, really. It discolors. It can crack from thermal stress, but it still can hold quite a high, handle quite high temperature. And more importantly, it handles direct plasma bombardment fantastically, which is really unusual for an SLA print. Because it's not a solid ceramic, it is just ceramic embedded inside the SLA resin. You wouldn't think that it would last so well up against the direct plasma bombardment, but it's worked so well that I'm probably going to continue using this for future cathode developments, just because it's handled it really nicely. And that'll go from anywhere from scaling from really small to larger cathodes for larger Hall thruster systems. So this allows me to design and build a custom cathode without, again, any custom ceramics. Any ceramics that are in here are, again, McMaster-Carr ceramic washers, and allows me to actually develop or design fuel feed lines directly inside the cathode. So this is bolted onto the thruster flange, which the Hall thruster is machined into, and there's a little fuel feed hole here. And there's a fuel channel that's actually 3D printed right into the actual cathode housing itself. So I think a very powerful testament to the abilities of 3D printing for aerospace type applications. And then moving forward for active thruster components for things that are directly exposed to harsh conditions. I wouldn't use it for the actual insulators inside of a Hall thruster, because it still wouldn't be nearly as good as ceramic parts. But for external housings and stuff, I think it's proved itself very nicely. So I think that's actually about everything for this kind of unboxing and design overview. Again, we have the AHT1-PQ. As far as I'm aware, the first ever PocketQube compatible Hall thruster, and probably the smallest full Hall thruster system actually designed. So hopefully I will be working on getting this system up and running hopefully this weekend. We have another question. For commercial versions of the thruster, will you need to consider shielding? So I guess which type of shielding do you mean? Do you mean like thermal shielding? Do you mean environmental shielding? Magnetic shielding? Because in terms of, I have considered possibly some environmental shielding for the electronics, just to kind of enclose them and protect it from any backstreaming plume or anything like that. The one thing about adamantane plumes that I've found is because it's a hydrocarbon, the plasma plume is actually quite dirty. It's a non-conducting film that forms, so there's no risk of any shorting or anything, but it's definitely an interesting challenge to have to deal with is because the plume itself is dirty, but that shouldn't actually affect the electronics directly. So I guess in terms of the shielding, for the question, magnetic. So because the thruster itself is so tiny and the magnetic circuit is concentrated within this area, I don't think magnetic shielding should really be necessary, just because the entire housing is steel, and the loop is enclosed within the thruster between the poles. So because the magnets are directly embedded inside the steel, because the pole pieces are so close and closed in, there really shouldn't be any or very much stray fields externally. And if there are some stray fields out here, that stray fields will be pretty minimal, and there shouldn't really be anything kind of lower or off to the sides just because of how thick the actual thruster is compared to the actual magnets itself. So I don't think magnetic shielding would actually really be necessary for this design. For much larger systems, especially systems that use actual coils to generate the magnetic fields, you might need more magnetic shielding. And there is actually magnetic shielding in terms of optimizing the field within the channel. So that's to help increase efficiency. But again, for this type of system, I'm not as worried about that type of optimization, just because it wouldn't be able to be practical to implement at this scale unless I start going into some super custom housings. Like for super small Hall thrusters where the housing is only a few millimeters in diameter, those are usually, I've seen them 3D printed or 3D or sintered, at least 3D sintering with custom magnetic material. So those are actually quite a bit more advanced and costly than I want to do. And realistically, I don't need the Hall thruster head to be that small, just because it's nice to have a Hall thruster head that can be scaled anywhere from PocketQube to larger CubeSat class satellites. So I think that's about it for this full reveal. If there's any final questions or anything, and definitely on social media, I'll be posting some updated pictures of each of the parts and the preliminary assembly, and then hopefully this weekend, if I can get everything wired up and put together and everything checks out, then we are looking at hopefully the first ignition test. That will also be live streamed with live chat on, so everyone can kind of see how that goes. And because that's the first time I'm ever running the system, there will definitely be some unique a learning curve, because every thruster that I operate always has a learning curve. They're quite interesting to operate, and really you can read a lot of text, you can read a lot of theory to explain how they work, but actually running them is a whole different thing, just because they're a very dynamic system. And there's different procedures and optimal ways of operating it. And even now, I'm not exactly sure how exactly I want to run this. If I want to open the valve first, if I want to turn on high voltage first, the heater first. So there'll be a little bit of playing around with how this thing will actually be operated. So once again, thanks everyone who decided to show up and see this reveal. Some really awesome questions were asked throughout this whole thing, so thanks Tejas for all your awesome questions. I think that really covered a lot of major areas and general concerns that you would typically think of for Hall thrusters. And because this system is very unconventional, a lot of the concerns for typical Hall thrusters would be probably different and not necessarily apply to this. So it'll be quite an interesting challenge to actually see if this thing operates. I'm expecting it to operate much simpler and easily and more reliable than all my prior thrusters to date, but you know, first prototypes never operate exactly how they're supposed to or expected. So either way, if the first test succeeds or if it fails, it'll be a huge learning experience, and every test is always informative regardless if something explodes, which did happen during one of my prior Hall thruster tests. I had a power supply literally explode in the vacuum chamber, or if we have ignition. So again, thanks everyone for showing up, and there will definitely be a lot more updates to come with this system as I gear up for ignition testing, and hopefully if this all goes well, we might actually see some opportunities open up to fly this thing in orbit in quite a soon time frame. So it'll be a lot of exciting stuff to hopefully come up if this thing is actually proven operational. So thanks again. Of course, you can always reach out over across all of this social media, and I'm always happy to answer any further questions about these systems. And I hope it was informative, and I know I can be sometimes long-winded in talking and explaining these things, but hopefully explained a lot of the basic concepts around the thruster, and we'll be seeing a lot more to come.